Hi everyone, in this video we will be going over the design of our pyrheliometer. We are Team Irradiant. A pyrheliometer is a device used to measure solar irradiance coming directly from the sun. There are also other sources created by sun indirectly, which are nearly impossible to leave out and thus affect the accuracy of our measurements. These devices are commonly used for climatological and solar energy research. A pyrheliometer main components are a quartz window, a black absorber, a thermopile or thermocouple, and the pyrheliometer tube, which defines the field of view. This diagram shows the main components. The pyrheliometer should have an acceptance angle as close to 0 degrees as possible so that the lens can bend and focus the light into the black body. The thermocouple then measures the heat from the black body, which is recorded for the system. Another important component for the pyrheliometer is the tracking system that should be able to follow the sun throughout the day. The purpose of our project is to design and manufacture a pyrheliometer at a much lower cost than those available in the market while keeping it within the accuracy. This will be built for Professor Fletcher Miller at San Diego State University so it can be used for future research.
For the project, we had a few constraints on how it needed to be built. First, the production cost must not exceed $1,000. This was one of the main points, as professional pyrheliometers are thousands of dollars. Next, the opening angle must be less than 2.5 degrees. It must accurately follow the sun and be within 5% accuracy of competitors. It must capture radiance within the spectral range of 200 to 3,500 nanometers, and must be able to withstand temperatures between 20 to 120 degrees Fahrenheit and be weatherproof. For the objectives, it should also have a backup method for tracking the sun on a cloudy day. So it should follow the sun based on resistors on the amount of light. And then it should also be able to sun even when there is clouds in the way. For the timeline, for the first 4 weeks of this semester, we were trying to figure out the project assignment, and then the next 6 weeks we were dedicated to research. And then the 4 weeks after that was designing the project itself. And then this past week we've been working on the presentation, and the week after we will be working on finishing the report. During break and for the first 5 weeks of next semester, we'll be planning on manufacturing. And then after that, the next 6 weeks will be used for testing and troubleshooting to make sure our project actually works. And then the last 4 weeks will be used for the report and the presentation. For research, one of the first things we did was we had to gather a further understanding on how a pyrheliometer works, as well as the components and the functions of the system. Following up on that, research was done on the optics needed for the system. In our case, we're using a spheric acrylic lens that helps us focus the light from the opening to the thermocouple at the bottom of the system. Another piece that we had to research more on in depth was the stepper motor and how to control it through Arduino. The stepper motor had to be very precise for this project. It had to have had to have movements within 1/10 of a degree.
Based on our research, we were able to put together the most important components of a pyrheliometer, and we will be discussing them in the next slides. For the stepper motor, we chose a model NEMA 23 with a step angle of 1.8 degrees. We picked a high torque motor because microstepping requires additional torque to stay accurate. For our controller driver, we chose the TB6600 stepper motor driver, and this part will be connected to a power supply to give power to the motor.
The tracking system will be controlled with an Arduino Uno R3 microcontroller. This is going to be used to program the motor and controller driver. A power supply will be also used to provide electric power for the microcontroller and the Arduino to move the stepper motor. These are examples of the sensors that we will be using to sense sunlight and follow the sun, and the thermocouple that will be placed inside the tube for the irradiance measurements. Based on our research, this is a schematic of the circuit diagram used for the setup of the tracking system.
For the pyrheliometer itself, the first part is the data acquisition device. This is a USB 6210 National Instruments, and this gets the data from the thermopile and records down the irradiance. And then for the lens, we use an aspheric acrylic lens NT48-184, and these are the dimensions we used for that best suited our pyrheliometer. And then for the thermocouples, we needed 2 of them. One was for measuring the temperature inside the tube, and the other was for measuring the temperature at the black body or the receiver disk. And those are the names of those. For the material selection, we decided to make most of ours out of anodized aluminum. This was because it had very good resistance to corrosion and wear, and making it weather resistant and perfect for our design. Another reason we picked it is it's lighter than most of the other metals that we were looking at, which is very helpful for our design. And then it also has a strong surface, which helps its durability and the longevity of the tool. For assembling the parts, the copper receiver disc will be attached to the center of the pyrheliometer through soldering, and the remaining parts will be attached using bolts, screws, rubber gaskets, O-rings, and L-brackets.
Here are some of the calculations that we considered important to discuss. We have been mentioning about the aperture angle and that it had to be at least 2.5 degrees, but this is where it comes from. It is the arctan of the radius of the sun over the distance sun to Earth, which gives around 0.5 degrees. This is the minimum angle that we are supposed to have, and the maximum angle of acceptance should be 4. So this angle is not only difficult to achieve, but it is also not preferred as it limits the amount of circumsolar radiation the device will record. So for our calculations, we're using an angle of 2.5 degrees. The next equation is the equation that gives the radius of the receiver disk. Using the given specifications on the lens, the back focal length and the diameter of the lens were provided, and we were able to get a radius for the receiver disk of 4.35 millimeters, or around 8.70 millimeters diameter. Now we will discuss these SolidWorks assemblies. This is the pyrheliometer full design. At the bottom, we have the box where the microcontroller, the driver, and the Arduino will make the solar tracker rotate. And then at the side, we have a box that contains the same parts, but these parts are going to make the pyrheliometer tube move up or down. These are the separate assemblies for the pyrheliometer and the solar tracker.
These 2 following clips show the tracking system movement in the pyrheliometer attached. The first one shows the movement in the east-west direction, and the second one shows the north-south movement. Before we end, we would like to thank our sponsor and advisor, Dr. Miller and Dr. Moon at San Diego State University, for guiding us through the design process. Thank you guys for watching.